In this video, we take you through the comprehensive installation and commissioning process of a 300 TPD, tons per day, Membranesbioreactor, MBR, plant, with a special focus on the MBR module guiding rails installation. This critical component plays a vital role in ensuring the smooth operation, maintenance, and longevity of the MBR system. Key highlights of the MBR module guiding rails installation. Material and construction. The guiding rail structure was constructed using high-quality mild steel I-beams, chosen for their exceptional strength, durability, and load-bearing capacity. The use of mild steel ensures the structure can withstand the harsh operational environment of the MBR plant, including exposure to moisture and chemicals. The structure features 4 horizontal bars, meticulously aligned and welded to provide a stable and robust framework. These horizontal bars are strategically positioned to ensure proper alignment and support for the MBR modules during installation, operation, and maintenance. The primary purpose of the guiding rail structure is to facilitate the lifting and handling of the MBR modules during cleaning and maintenance. The design ensures that the modules can be safely and efficiently lifted out of the reactor tank for routine cleaning, membrane inspection, or replacement, minimizing downtime and maximizing operational efficiency. The installation of the guiding rails was carried out with precision and attention to detail. The I-beams were carefully measured, cut, and welded to ensure perfect alignment and stability. The structure was securely anchored to the reactor tank framework, ensuring it can handle the weight of the MBR modules and the forces exerted during lifting operations. The guiding rail structure enhances the overall efficiency of the MBR plant by simplifying maintenance procedures and reducing the time required for module handling. Its robust design ensures long-term reliability, reducing the need for frequent repairs or replacements. The MBR module guiding rails are a critical component of the MBR system, ensuring the seamless operation and maintenance of the plant. By investing in a well-designed and properly installed structure, we ensure the longevity and efficiency of the MBR plant, ultimately contributing to the success of the wastewater treatment process. The combination of MBR, Membranesbioreactor, guiding rails with a 1-ton capacity chain block is a practical solution for lifting and positioning MBR modules, especially during membrane cleaning or maintenance tasks. Here's a more detailed breakdown of the installation and maintenance procedure for this system. Rail alignment. The guiding rails need to be precisely aligned with the movement path of the MBR module. Ensure they are straight and securely mounted to the ceiling or overhead structure, making sure the distance between the rails is appropriate to guide the MBR module safely. Attachment points. Install attachment points or hooks for the chain block on the supporting structure above, ensuring they are rated for at least the weight of the module, typically around 1 ton or more, depending on the module size. Chain block installation. Position the chain block above the MBR unit, directly aligned with the module. The chain block should be mounted to a sturdy beam or structure with proper safety measures in place. Secure the chain block. Attach the lifting chain to the lifting point of the MBR module, ensuring it is securely fastened. Before lifting any equipment, test the lifting system without the MBR module to ensure the chain block, rails, and supporting structure are functioning properly. Weight check. Ensure the system can lift and move the modules smoothly along the rails with no undue strain or obstruction. Maintenance procedure. Regular inspection. Rails and chain block. Clean the rails, chain block, and lifting mechanism periodically to remove debris, dirt, or any buildup that could impede movement. Lubricate moving parts as per the manufacturer's recommendations. Chain and hooks. Ensure the chain is free from rust and is lubricated. Also, inspect the hooks for any cracks or wear that could compromise safety during lifting operations. Periodically, perform a load test to ensure the lifting mechanism can handle the rated load, 1 ton. This can involve lifting the MBR module to its usual height and checking for any signs of difficulty or strain on the system. Test the safety features such as the emergency brakes or limit switches to ensure proper functionality. If any part of the chain block or rails becomes damaged or worn beyond a safe level, it should be replaced immediately. Always use original parts for replacements. If the system uses wear indicators, replace components before they reach their wear limits. Over time, the chain block may become misaligned. Recalibrate the block and check the chain tension to avoid uneven lifting, which can cause strain on the system. If the rails begin to show any deformation or misalignment, adjust them accordingly to ensure proper module movement. Always ensure that the lifting operation follows proper safety guidelines. Workers should wear appropriate personal protective equipment, PPE, and only trained personnel should operate the chain block and lifting system. Use the chain block at a steady pace to avoid sudden jerks or shock loads on the system. Controlled movements ensure both safety and minimal wear on the components. The combination of MBR guiding rails and a 1-ton chain block is an efficient method for lifting and maintaining MBR modules during cleaning. Regular inspection, cleaning, and preventive maintenance will ensure that the system continues to function properly and safely over time. MBR Module, Membrane Bioreactor, System. Purpose. The MBR module is part of a membrane bioreactor system used in wastewater treatment. Its main purpose is to filter water, separating solids and contaminants from the treated water, while also providing biological treatment. It combines biological degradation, through activated sludge processes, and membrane filtration, through micro or ultrafiltration membranes, in a single integrated system. The MBR system is commonly used in municipal wastewater treatment for treating sewage, industrial wastewater treatment for various industries like food processing, pharmaceuticals, and chemical manufacturing, water reuse applications, providing high-quality treated water for reuse. Properties. Membrane type. The membrane can be microfiltration, MF, or ultrafiltration, UF, which allows for fine filtration, effectively removing suspended solids and microorganisms. Porosity. The membranes typically have pore sizes in the range of 0.1 to 0.4 microns, capable of filtering bacteria, suspended solids, and large pathogens. Material. MBR membranes are typically made from materials like polyvinylidene fluoride, PVDF, polyether sulfone, PS, or polypropylene, PP, offering resistance to fouling and corrosion. Size and shape. Membranes can come in different forms: flat sheet, hollow fiber, or tubular. Each type offers specific advantages in terms of filtration efficiency and ease of cleaning. Operating conditions. MBR modules operate at pressures typically between 0.1 and 0.4 bar, and they are designed for continuous operation. Operation and behavior. Biological treatment. In an MBR system, microorganisms, bacteria, fungi, etc., degrade organic matter present in wastewater. This process is similar to traditional activated sludge treatment, but with the added benefit of membrane filtration to separate the biomass from the treated water. Flux and fouling. The filtration process, also known as flux, is defined as the volume of water filtered per membrane area per unit of time. Over time, membrane fouling, due to solids buildup, biofilm, or scaling, can reduce the flux rate, requiring regular cleaning and maintenance. Installation. Location. The MBR module is typically installed in a reactor vessel where wastewater is pre-treated before membrane filtration. It is usually submerged in the biological tank or integrated into the treatment unit. Pipeline connections. The wastewater inflow and effluent outflow must be properly piped to the module for continuous treatment. The system may also require recirculation pumps for sludge handling. Electrical and control systems, power supply and automated control systems, for backwashing, cleaning cycles, etc., must be installed and properly calibrated to ensure the system operates smoothly. Maintenance. Regular cleaning. cleaning is required periodically to remove fouling materials like biofilm, sludge, and scaling that accumulate on the membrane surface. There are typically two types of cleaning. Chemical cleaning, using acid, alkali, or detergents to remove organic or inorganic fouling. Physical cleaning, using backwashing or air scouring techniques to dislodge particles. Monitoring, routine monitoring of transmembrane pressure, TMP, is essential for tracking membrane performance. A rise in TMP indicates that cleaning is necessary. Replacement, membranes have a lifespan and may need to be replaced when fouling cannot be effectively reversed through cleaning. Diffuser disc system. Purpose. The diffuser disc system is used in wastewater treatment and aeration processes. Its primary purpose is to distribute oxygen into the water in a controlled and efficient manner, supporting aerobic biological processes in activated sludge tanks, MBR tanks, and other bioreactors. Diffusers ensure the efficient transfer of oxygen to microorganisms, which helps in the breakdown of organic contaminants in the wastewater. Properties. Design. Diffuser discs are often made from durable materials like rubber, ceramic, or plastic, which can withstand the harsh conditions in wastewater treatment plants. They consist of a perforated or porous disc that releases air or oxygen. Pore size. The pore size of the diffuser disc can vary. Smaller pores tend to produce fine bubbles, which increase the oxygen transfer efficiency, while larger pores create coarser bubbles. Shape. They are typically round or flat discs with multiple perforations across the surface. The specific design of the diffuser, e.g., surface area, hole size, affects the bubble size and overall efficiency. Materials. Common materials include EPDM, ethylene propylene diene monomer, or ceramic. EPDM diffusers are more commonly used for long-term performance and resistance to fouling. Operation and behavior. Aeration. The diffuser disc system injects air or pure oxygen into the wastewater. The air bubbles rise through the water column, transferring oxygen into the water and promoting the aerobic degradation of organic matter by bacteria and other microorganisms. Oxygen transfer efficiency, OTE. The effectiveness of the diffuser depends on the bubble size. Fine bubbles tend to have higher surface area and improve oxygen transfer efficiency. The design and maintenance of the diffuser system directly affect the system's efficiency. Pressure requirements. Diffuser discs generally operate at low to medium air pressures. Too high a pressure can cause excessive wear, while too low a pressure may result in insufficient aeration. Fouling and clogging. Over time, diffuser pores can become clogged by biofilm, sludge, or scaling, reducing oxygen transfer efficiency. Routine cleaning and maintenance help mitigate this issue. Installation. Placement. Diffuser discs are typically installed at the bottom of aeration tanks or bioreactors, where they are connected to a blower or air supply system. Spacing. Proper spacing of diffusers ensures uniform distribution of air and avoids areas of high or low oxygen concentration. The system may include several manifolds or pipes to connect multiple diffusers. Alignment. The diffusers should be installed at an angle or orientation that maximizes oxygen transfer and minimizes backflow or clogging. Maintenance. Cleaning. Diffuser discs need to be cleaned periodically to remove biological buildup, sludge, or mineral deposits that can clog the pores. Cleaning can be done using air scouring, blowing air through the system to dislodge debris. Chemical cleaning, using acids or other cleaning agents to remove scale or biofilm. Inspection. Regular inspection should be carried out to check for any damage to the diffusers or air supply lines, which could lead to inefficient aeration or system failure. Replacement. Over time, diffuser discs can wear out due to constant exposure to chemicals, air pressure, and biological fouling. Worn or damaged discs should be replaced to maintain aeration efficiency. Blower maintenance. The air supply system, typically a blower, should be regularly inspected and maintained to ensure it is delivering air at the required pressure. Inspection. Regular inspection should be carried out to check for any damage to the diffusers or air supply lines, which could lead to inefficient aeration or system failure. Replacement. Over time, diffuser discs can wear out due to constant exposure to chemicals, air pressure, and biological fouling. Worn or damaged discs should be replaced to maintain aeration efficiency. Blower maintenance. The air supply system, typically a blower, should be regularly inspected and maintained to ensure it is delivering air at the required pressure. Fouling control. Membrane fouling occurs when solids, bacteria, or biofilm accumulate on the surface of the membranes, causing a rise in transmembrane pressure, TMP, and reducing filtration efficiency. Air scouring, aeration, and periodic cleaning are essential for controlling fouling. Pressure monitoring. TMP is continuously monitored, and when it reaches a predefined threshold, the system may initiate a cleaning cycle or backflush. 2. Commissioning of the MBR plant. Commissioning steps. Commissioning is the process of setting up and testing all components of the MBR plant before it begins full-scale operation. This ensures that all systems are operating as expected and that the plant is ready for continuous operation. Pre-commissioning checks. Visual inspection. Check all physical components, such as pipes, pumps, membranes, aeration systems, and control panels, for installation errors or damages. Electrical and instrumentation setup. Ensure electrical systems, controllers, sensors, and instrumentation, pressure, flow, and quality monitoring, are correctly connected and configured. Initial system startup. Flush the system. Before introducing wastewater, flush the system with clean water to ensure there are no blockages or contaminants in the pipes and membranes. Fill bioreactor. Gradually fill the bioreactor with the wastewater influent, ensuring no airlocks are present in the piping system. Biological seeding. If the system is a new installation, inoculate the bioreactor with activated sludge from an existing plant or use synthetic seeding to establish the microbial population needed for biological treatment. Aeration startup. Begin aeration in the bioreactor to encourage microbial activity and promote healthy biomass growth. Membrane integrity testing. Conduct membrane integrity testing to ensure there are no leaks or faults in the membrane modules. This can be done by applying a test pressure and checking for any drops in pressure. Membrane wetting. Wet the membranes with clean water to ensure proper functioning before they start filtering actual wastewater. System startup and stabilization. Gradually introduce influent to the system and increase the flow rate to full design capacity. Allow the system to stabilize biologically, adjusting aeration rates, sludge recirculation, and other parameters to maintain optimal microbial growth and membrane filtration performance. Monitor key parameters like dissolved oxygen, dew, pH, and temperature to maintain ideal conditions for biological treatment. Performance monitoring and adjustment. Regularly check the membrane filtration performance, including flux rates and TMP. Adjust operational parameters, aeration, recirculation, flow rates, to optimize treatment performance. Begin monitoring effluent quality to ensure it meets regulatory standards. Maintenance of the MBR plant. Proper maintenance is critical to ensuring the long-term efficiency, reliability, and performance of the MBR plant. There are various maintenance tasks related to both the biological and membrane filtration systems. Routine maintenance. Monitoring and data logging. Continuously monitor key operational parameters, such as transmembrane pressure, TMP, flux rate, effluent quality, BOD, COD, TSS, and aeration efficiency. Log operational data regularly to track trends and identify any performance degradation early. Aeration system maintenance. Check and clean air diffusers to prevent clogging and ensure efficient oxygen transfer. Inspect and maintain blowers, valves, and aeration pipes to ensure proper operation and airflow. Sludge management. Regularly check and adjust sludge recirculation rates to maintain a healthy microbial population. Periodically remove excess sludge from the system to prevent overaccumulation, which could affect membrane performance. Membrane cleaning. Chemical cleaning. When TMP increases, use chemical cleaning procedures to remove fouling. Cleaning chemicals may include acids, alkalis, or detergents, depending on the type of fouling, e.g., organic fouling, scaling, biofilm. Physical cleaning. Regularly backflush or perform air scouring to reduce fouling accumulation on the membranes. Cleaning frequency. The frequency of cleaning depends on the type and concentration of pollutants in the influent. Frequent cleaning may be needed if influent is highly fouling. Membrane replacement. Membranes wear out over time due to fouling and the mechanical stresses of filtration. Regularly inspect membranes for physical damage, cracks, or excessive fouling. If cleaning does not restore membrane performance, consider replacing damaged or heavily fouled membranes. Backwashing and flushing. Periodically backflush the membrane modules to remove particulate buildup. This involves reversing the flow of permeate through the membranes. Flush the system with clean water after backwashing to ensure there are no residues left behind. Cleaning and replacing filters. The pre-filters used in the influent line may need periodic cleaning or replacement to prevent debris and large particles from reaching the membrane module. Preventive maintenance. System calibration. Ensure that flow meters, pressure sensors, and quality sensors are calibrated regularly to provide accurate readings. Routine equipment checks. Inspect pumps, blowers, valves, and other mechanical equipment regularly for wear and tear. Lubricate moving parts to prevent damage. Structural integrity checks. Inspect the structural components of the plant, including the tanks, piping, and supports, for signs of corrosion, wear, or damage. Troubleshooting. If the plant is experiencing issues, troubleshooting involves low membrane flux, check for fouling, clogging, or incorrect aeration. High transmembrane pressure, TMP, investigate for fouling, improper cleaning, or membrane damage. Effluent quality problems, ensure proper biological treatment, aeration, and membrane integrity. The operation, commissioning, and maintenance of an MBR plant require a well-coordinated approach that includes initial setup, regular monitoring, and proactive maintenance. Key to the success of the MBR plant is maintaining an optimal balance between the biological and filtration processes. Routine cleaning and membrane management are critical to maintaining performance, and effective troubleshooting ensures the plant continues to operate efficiently throughout its life cycle.